In the following lecture, I would like to give a short introduction into the Muskingum Method, which is a special flood routing method, and I think it's a very classical one, but I don't like it very much, and I would like to explain why I do not like this method very much. So, what is the aim? What is the aim? First of all, unfortunately this is in German, I would like to show you classical flood events. This is the time, and this is the free surface elevation. When we look at a certain point upstream of the river, then we get something, then we could get something like the blue line for a flood event. The flood is rising in a smaller amount of time, and then it's falling down to the base level again, but in a little bit larger amount of time. When you look a little bit more downstream, then you have two effects. First of all, of course, the flood is coming a little bit later. The flood is coming a little bit later, so when you look on the time scale, here the maximum of the flood rise is here a little bit later, and this is called retardation. Verzögerung in Deutsch. This is called retardation, and of course, when we want to manage floods, then we have to know this kind of retardation, because then we know, oh, there was a flood in Cologne in Germany, for example, and we want to know when is the maximum of the flood coming in Düsseldorf, or vice versa, or as in every river on earth. So we want to have a fast estimation of the retardation time for every town or cultural heritage downstream of this point. Yes, and when we look again a little bit more upstream, then we again have, of course, a time gap. The flood is coming again a little bit later. This is again retardation, but you see a second effect. The second effect is when the river cross section is everywhere the same, then we have an attenuation, eine Dämpfung in German, an attenuation of the flood, which means we have a lower level downstream, and when we look again a little bit more downstream, then we have a even more lower level of this flood events. So a flood is becoming less and less dangerous when we look downstream. This is a good thing, but, of course, we have tributaries, Nebenflüsse, coming into the main river and increasing the flood again. We have some changes in geometry, some meanders or whatever, some wears, which changes this. So this is not, of course, not a natural law that a flood is attenuated during its course through a river. It can also go up. For example, the most dramatic thing nowadays is the Isar River, coming in Bavaria into the Danube River, and most of the floods in the Danube River are not really or not so high, but when the Isar is as a tributary is coming into the Danube River, then it is increased. So that is not a natural law. We're just thinking about a river which has more or less the same cross-section during its course. There's not a big groundwater or rainfall influence coming from the sides, and there are no tributaries. Then a flood is attenuated during the course. So it is retarded and attenuated. And when we want to calculate by a very, very, very fast calculation, because we need it during flood operations, that we know when the flood is at a certain point here, it is measured here, how long does it take that it comes to that point, and how much is the attenuation. And one of the classical methods to calculate this is the so-called Muskingum Method, coming from the 60s of the last century, when computation methods started, and this was one of the first computation methods, and I would like to explain this method a little bit. This method starts, of course, with mass balance. With mass balance as we learned it in our other lectures. So, the mass balance in a river compartment is the volume during time step n+1 minus the volume at time step, the total volume in a river compartment at a certain time step n divided by delta t. This is a derivation of volume change during time. And this is the difference between incoming discharge and outgoing discharge. If the incoming discharge is larger than the outgoing discharge, then the water level will increase. This is a positive number on the right hand side. And if the outgoing discharge is larger than the incoming discharge, then the water level will decrease because the left hand side is negative. This means that the next volume, total volume of the river compartment is smaller than the river compartment before. So this, or when we're talking about numerics, this is nothing else than a Eulerian scheme to solve a time-dependent differential equation. This is correct. I have no critics on that. So the next question is, how do we calculate the incoming discharge and the outgoing discharge? Should we calculate it at the time step n, so where we know all our things, or should we calculate it at the time step n+1? And the best thing is to take an average between time step n and time step n+1. So for q in, we replace q in by the incoming flux at the new time step n+1 we want to solve, plus the old time step q in at time step n divided by 2. So this is just the average, And of course, we do the same with Q out. So we replace this here with Q out. We multiply the equation with delta T, and we put this on the other side. So this is a classical. So this is the volume at the next time step the total volume of in the next time step is the old volume plus the average incoming flux times delta T minus the average outgoing flux divided times delta T. So this is also correct. As a numerical scientist, I would say this is a Crank-Nicholson scheme. And of course, this is very exact. This is exact to the second order. Nothing to complain about. But the next thing is what we are looking here at. We want to predict discharges. Discharges in a downstream cross-section at a later time discharges. Here I have water levels, but I should also, the discharges look more or less the same. So we want to calculate discharges. So what Muskingum method is now doing, it is replacing the volumes in a river compartment, the volume of a river compartment with something which is depending on the discharge. And the idea is replace the volume of a river compartment by the outgoing discharge times a constant, or times a parameter. So the volume of a part of the river can be calculated from its outgoing discharge. And this, of course, is a huge simplification. And when you look at the papers, they always say it comes from the outflow from a reservoir. Even for a reservoir, this is not correct. So when this is a reservoir, this is the outgoing cross section, then we have, according, for example, to Dubois, we have something like the outflowing cross-section can be calculated according to Torricelli, and the falling height, the difference between the level in the discharge and the level here, multiplied by the outflowing cross section. So when we look at this, the discharge is not proportional to the volume of the reservoir. The volume of the reservoir would be height times bottom cross section, height times bottom cross section. But Muskingum and all the hydrologists who say there is a linear relation, linear reservoir theory, a linear relation between volume and outgoing discharge assumes it. And this, in my opinion, or of course we now knew it, is as a matter of fact not correct. Absolutely not correct. Yes, the next thing is that the method is changed then to river compartment. A river compartment, this would be correct. Well, they say this would be correct in the sense of Muskingum. This would be correct for a reservoir, but for a river discharge, for a river compartment, where we have a different free surface elevation here and here, we have an incoming flow and an outgoing flow. They calculate the volume in this part of the river by the ingoing flux. First of all, they start for reservoir, taking the volume proportional to the outgoing flux. Then they take a river compartment, so with in and outgoing flux, and then they say the volume is, or then he said the volume is proportional to the ingoing flux. And this is the idea behind this is very easy. Just look at the blackboard. We have an ingoing flux here. The ingoing flux can be divided into the outgoing flux, which is here, and the difference between minus ingoing and outgoing flux. So this part here is the difference between ingoing and outgoing flux. This is the flux is ingoing flux, but the same flux goes here out. Here comes a little bit more in, so the difference here is coming in I minus O plus O, which is I, and here goes out O. So and the idea is now to say, this is really strange, and I would like to explain it in that way because it is strange. It is strange. The idea is to say that the total volume, again, is proportional to the flux, but now to the ingoing flux, which is Q out, because it goes out here, and 1/2, because this is a triangle, 1/2 ingoing minus outgoing flux here. So this is weighted by 1/2 because this is a wedge, ein Keil in Deutsch. Because this is a wedge, and the idea is to say the total volume in this part of a river is proportional, can be calculated as the ingoing flux times K, and the ingoing flux is divided up in the flux which also goes out, and the difference I have to weight with 1/2, because when it's a very small compartment, then it's a triangle. Yes. Ladies and gentlemen, I think this is very old-fashioned, very old-fashioned. This has nothing to do with hydraulics, but it is always just, let me put on the light. We forgot, I think. This is always taken in hydraulics to be true, and what is done in hydraulics, it was changed and changed and changed. A wrong idea was changed in all the parameters until it's true. So the first thing was, of course, when we look at this point, Q out minus 1/2 Q out is 1/2 Q out. 1/2 Q in plus 1/2 Q out. So, and then they changed, they said, this is here, we have to take this 1/2 and this 1/2, put another parameter in it, a weighting parameter. We do not take 1/2 and 1/2, we just take here 1 minus x and here plus x. For x is equal 0.5, this is the original formula. Just that we have another parameter for freedom in it. So we can change this parameter to get good results, and we can change this x to get good results. So this is the idea. So now we have the volume. Now we have the volume, two free parameters we can change. We can tune that we get the good results. Put this volume here in our original equation, which to my point of view is correct, absolutely correct, because it's just mass balance. Put it on this side here as the volume at the time step n plus 1, and here at the volume times n, and it gets, we introduce this and this equation as I wrote it here, one time here with q out at time level n plus 1, and with q in at time level n plus 1, one time with qn here and qn here, and we get a large equation, but very simple one, and which we can, where we can derive the outgoing flux at the next time step. So this is just, we change it a little bit, and then we get at the end, it's not absolutely not easy, the outgoing flux at the next time step is the ingoing flux at the time step plus the ingoing flux at the next time step minus the outgoing or plus the outgoing flux at the last time step here. So this is the Muskingum method with some parameters before it, and we can change x and k until it works quite well. Yes, so let us now sum up the method. We have a discharge, I always have here the depth, but it should be the discharge. We have a discharge at a certain point in the river, which here is at 37.5 kilometers. We have a discharge as a function of times. What we want to have is a black discharge a little bit downstream, or the red discharge a little bit downstream. One of the curves we want to have. So our ingoing flux is a blue curve, which we know at every time point. So we know ingoing flux at this point of time, this point of time, this point of time, this point of time, we have always the ingoing flux. And the question is, what is the outgoing flux? The outgoing flux at the next time step is a function of the both ingoing flux and the first outgoing flux. So in the first time step, we have to assume the outgoing flux, for example, to be the same as the ingoing flux. But when we want to have a start outgoing flux, then we can calculate all the next outgoing flux and the results, yes. And the results, I tried it. This is not Muskingum method, what I have here. This is Saint-Binon equations. And the result, when we just let it as it is, for a ingoing function like a sinus function. When we have a sinus function representing the flood wave, and then it is the original point, so I have something like the maximum of 100 plus a flood discharge of 100 cubic meters, the first sinus wave, and then I say when it's going down, takes the minimum of this. So this is my ingoing function, and when I implement it, then at a later time step, it really looks like this. It has a small mistake, and a lot of persons are thinking about this mistake. This is not correct, of course, and they found out that when I change the parameters before this three fluxes here a little bit, that they are always positive, then the sum must also be always positive, then it works. So this is the next change, but I don't want to go into the detail in the next change that is always positive here. But what you see is it comes a little bit later, and now by tuning k, we can change the time when it comes a little bit later. So with larger k, it needs more time. Yes, it has more retardation. And then with x, we can change the attenuation. So trying to change x, we get the attenuation. And the idea is now to have, for a certain flood event in the Danube River or in the Rhine or in every river on Earth, we can just calibrate the k and x one time between Cologne and Düsseldorf, for example. We know the k for the Rhine is that way and the x is this number. And for the next flood, coming a little bit different, we say take the same k and x and the method works. It works quite well. It works not so bad. But of course, as a matter of fact, it is, yes, I don't know which word is physically speaking totally wrong. I just programmed it. Here you see something like the ingoing flux 100 plus 100 maximum of a sinus wave. The outflowing flux for the first time step is the same as the ingoing flux. Then I take an x and an k, and then I calculate the next one, and I plot both. I don't want to show it to you here a little bit, and then I just start it, and you see it here, the result. So when I increase the k, for example, to 8,000 or whatever, then again I start it, and it gets a little bit more attenuated and a little bit more. The flood comes a little bit later. It looks a little bit bad here, of course, and it goes a little bit deeper here, so you have to try to change these parameters, and there are a lot of articles on that, how to change the parameters, how to get nothing like this, the negative or the values here and so on. But for me, this method has no physical correct basis, and I think we should improve this, or we should take other methods working on momentum balance. Mass balance in this method is absolutely correct, but as a matter of fact, the ideas behind Muskingum methods are, physically speaking, not correct.